here's a careful justification of what I was saying in the derivative intro part 2. If you have this cubic function, I was claiming that if you already know the derivative of x cubed is 3x squared, if you know the derivative of x squared is 2x, you know the derivative of a constant is 0, you can just put together the pieces in this very easy way. Well, let's go ahead and go through the limit calculation and see how that comes out. And if you want an even more careful and more general derivation, obviously that's what the book is for. One thing that we haven't done much of before is taking, first of all, this notation is somewhat new to us, but we've taken this limit as h goes to 0. We've usually called this letter a, because we've usually been thinking of this as a fixed number, so we use the beginning of the alphabet. But the whole point here is now to think of this as something that, as soon as we do this calculation, is going to be a variable, and we're going to be able to plug in, and we're going to get a function. And we've already gotten a little familiarity with the idea of a derivative as a function. So I'm really going to let this be from the end of the alphabet. It doesn't change the argument or the algebra one tiny little bit. It's just a little bit of a perspective change. Okay, so now I'm just going to copy this and put in the definition of the function everywhere. Okay, so let's see. If I take x plus h and I plug it into here, I'm going to get x plus h quantity cubed, which I'm going to have to deal with, minus 2 times x plus h squared plus 1 minus, and then in parentheses, really, really crucial parentheses, you're going to majorly not have anything work if you don't remember those parentheses. Let me even put the parentheses around this to emphasize that. Okay. Okay. So now, even after talking about how important those parentheses are, I'm going to mess with them. I'm going to regroup stuff. The key to this thing is the claim was that the x cubed part and the minus 2x squared and the plus 1 can operate kind of independently. And so I want to split those up completely separately. So I'm going to take these parentheses away. I'm going to take these guys, but carefully distribute the minus sign. Oops, that's a minus. Okay. And now I'm just going to group everything. I'm going to group the thing that came from x cubed together over here. Okay. And I'm going to put those in their own little parentheses. I'm going to take the thing that came from the 2x squared, I'm going to put it here, and then I'm going to factor out this minus 2. Okay, so I'm going to put these in parentheses. If I'm factoring out a minus 2, this turns back into a minus 1. And then this guy, of course, that's just going to die, which confirms that the constant is going to make no contribution. Okay, so now, let's see. I'm even going to be more aggressive at splitting it up. I've got a sum and a difference kind of stuff up here in the numerator. And the numerator of a fraction can always be split up. And so I'm going to separate this out into 3 separate fractions. I'm going to take this out. I'm going to create a new fraction with that in the numerator and h in the denominator. And then I'm going to subtract off 2 times a fraction with just this in the numerator. And I'll do that by just killing this guy off. Okay. And then finally, well, you know what? I'm just going to let the constant die. It's dead. We don't have to resurrect it. Okay. So here I've got one big expression, which is 2 fractions. I'm taking the limit of that. Here's where I get to use the limit laws. This is the kind of thing that's going to actually exist as a number. We'll see that in a minute. This is going to exist as a number. And so the limit of the difference of 2 things, totally fine to use the limit laws here. And so I'll copy it, but then I'm going to immediately start changing it around. I'm going to put in a limb right here, because the difference of the limbs is the limit of the difference. H goes to 0. And in fact, the limit of a constant times some function, I can take that guy out. Boom. And now we stop and look. We'll get the actual answer in a minute, but mainly the work is done here. Because what is this? This is exactly the derivative. This is what I would get for the slope of the tangent line of the cube function. Because this is just f, if f of x is x cubed, that's going to be f of x plus h, that's f of x over h. This is the derivative of the squaring function, because that's f of x plus h, that's f of x if f of x is the squaring function. And so it's really confirming that I'm just getting the contribution that I got from x cubed, and then minus 2 times the contribution from x squared. And now I just have to reconfirm what I had before, these calculations that seem to show that this was 3x squared and this was 2x. We got those off the calculator, so let's do this for real. We've actually really almost done these calculations, though. Okay, so this guy, I just need to cube this thing out. That's binomial x cubed plus 3x squared h plus 3x h squared plus h cubed, and then minus the x cubed. I don't really need the parenthesis anymore. Okay, and then this stuff, that's a square of binomial, and so it's that stuff. And then what do we notice? The x stuff cancels out, which is really nice. Oh, oops, that's not what I wanted. And I'll just do it fresh. Okay, so the x squareds, x cubes here cancel out. Why is that so crucial? It's because I need an h to cancel on the bottom, and otherwise it would not happen. Aha. Now there's a factor of h up here, and there's a common factor of h here. I'm going to just do that in place. I'm just going to factor out the h here and just decrease the power by 1, by 1, by 1. And I'm going to factor out an h here. Ta-da. And now I can carefully cancel those h's. It really is a common factor top and bottom. You don't just cancel like this h against just this h or just this h. It has to be a common factor top and bottom. But let me just go ahead and do that. I don't need the parenthesis anymore. Oops. And that's a 1 on the bottom. Yay! And now it's easy to take the limit. There's no problem. Now remember, x here is just anything, but it's not a variable as far as the limit is concerned. It's just kind of hanging out for the ride. It's going to get upgraded to a variable as soon as I'm done with this process, and I'm going to think about putting in different x's. But right now, you just want to think of it as basically a number, and h is the only thing where the action is going on with the limit. And if h is being set to 0, this guy's going to die. This guy's going to die. This guy's going to die. And what am I going to get? I'm just going to get 3x squared minus 2 times the quantity 2x. And that's exactly what we had before. So it's not so much this explicit answer that's of interest here. It's this process that says that if I had a sum of things, each of those contributions were separate. And the constant dies, this contribution was separate, this contribution was separate. So once we do this calculation that x cubed becomes 3x squared and x squared becomes 2x, we never have to do that limit calculation again. We can use those as building blocks. And then anything made up out of them as the sum or difference is going to be fine. One repeat of a warning, though. Remember, one of the rules was that a constant, where was it? If a function is multiplied by a constant, that constant just comes through the calculation. It comes out. It doesn't go away. It just comes out. So the derivative of minus 2x squared is minus 2 times the 2x, which was derivative of x squared. But only if it's a constant. We will have what's called the product rule for the product of two variable functions soon, but it's more complicated. And don't assume that the derivative of a product is the product of the derivatives. That's just not true in general. Okay.